I'm Yokota Tatsuya. Today I will talk about the title of Plug and Play of Least Squares-Based Tensor Decomposition Algorithms for Tensor Learning. First, I will show some brief self-introduction. So I was graduated from Tokyo Institute of Technology. And during my doctoral course student, I was in RIKEN Brain Science Institute under the supervision of Professor Chihotsuki. And in that period, so many friends in this. And after 2 years postdoc working in RIKEN Brain Science Institute, after that I moved to Nagoya. So now I'm research about also tensor learning, but also medical image processing applications. So this is a summary of my project since 2019. Because I became the visiting researcher in RIKEN AIP since 2019. Usually I summarized the project, the 4 projects. One is Hankeization in tensor learning. This topic is I had the poster in the other room, so let's discuss later. But so I do not talk about this here. Also, sparse regularization in tensor learning, and algorithm development in tensor learning, and medical imaging using tensor learning. So today I will talk about this one, third one, algorithm development in tensor learning. Maybe for some people, my talk is very basics, and sometimes obvious thing I talk, but please. Okay, so also during this period, I wrote the chapter in the book. So this is a book and title of Tensors for Data Processing. So I wrote chapter 11, Tensor Methods for Low-Level Vision. I wrote this chapter with Dr. Cesar and Dr. Chibi. And also I wrote the Japanese textbook for the tensor data analysis in Japanese. I'm sorry, so this is written in English, but I will maybe translate this in the future in English. I also wrote the very basics of tensors. This is uploaded in archive, and in this archive paper, I very gently explain the graph representation of tensors like this. If you are interested, please check this one. Okay, so from the basics of tensor learning. So tensor learning have several flow of processing. This is one of the typical flow. First, we have data, but data is not tensor. Sometimes this is tensor, but it's okay. This is vector and some other table of data, something like this. But after that, we convert the data into the tensor. So this is important how to represent the data as a tensor. So how to construct tensor is very important in applications, because in this step we need domain-specific knowledge So data have low rank structure is very important in tensor representations. So sometimes one of the important perspective is approach is Hankelization. So Hankelization but I do not explain detail of Hankelization here. Please compose the data. And then we apply tensor decomposition, and we can obtain the result. Noise reduction, imprinting, background loading, something like this. And this is the second flow. So it's like a more machine learning approach. We have data, the pair of xi and yi, and we want to model the relation between x and y. Then we consider some mathematical models and input x and output some prediction of y. And we evaluate the measure using loss functions between yi and inference. In this case, the parametric model have core tensors. Then we want to optimize these core tensors in learning. This is a tensor learning problem. And as a result, we can obtain many applications. Okay. And so one of the goals in tensor learning is approximation function. For example, we consider the brain imaging. The brain image is originally a continuous function. We have 3 axes, x1, x2, x3. And inputting these 3 axes, continuous values, then we can get some one real value. However, in many cases, we cannot obtain the continuous function, but we consider to reconstruct the tensor. This kind of this is represented as the sampling. So we consider the grid data, and the tensor learning is to construct the. We want to know this original function. However, we do not have the data, but we have some limited number of data about unknown function. Then we learn tensor y from this data. So in this case, the tensor y is have 3 modes, and this third order tensor is represented as this one, like this, in graphical notations. And if we want to pick up the 1 entries from this tensor, then in this case, we just consider the indices. IJK index is, this is regarded as a discrete function. Okay, so let's consider this process by using the in graphical notations. So we have this tensor, and we want to extract the value of IJK index. So in this case, this process can be formulated as inner product between y and some tensor E IJK. Tensor E IJK is one hot tensor. For example, it is so only IJK index is 1. Other elements are all entries are 0. This is one hot tensor, but this one hot tensor is actually rank 1. For example, maybe this with rank only 1 matrix that one hot matrix can be decomposed into one hot vector like this. So this is just I wrote the ij like this. So then this process can be represented as like this in graphical notation. Okay. So next, so consider the different thing, little bit different thing. We want to know the continuous function and run a tensor W. It's same. However, so in this case, we have to obtain the pick up one value from this tensor in this continuous function. So in this case, we run a tensor, and after running, we obtain this tensor, and then we consider basis function phi, and also basis function phi can be decomposed as rank 1 basis. In this case, we can formulate this process also as the inner product between tensor W and phi 1, phi 2, and phi of x3. Okay, so the tensor model have can represent the function, also represent the discrete function and the continuous function. The problem, essential issue of tensor learning is cause of dimensionality, and the order of tensor is increased, and the number of entries are exponentially increased. But this is a fundamental problem in tensor learning. Then we will decompose this tensor W into the product of small core tensors like this. In this case, we can reduce the number of parameters, and it can be tractable. Okay. So now I will introduce the one of so good big landmark studies by the Stoudemire, 2016. This is in this work, he applied the tensor networks into the pattern classification problems. So he used the model TT decomposition for the W and minimize L2 loss, and optimization using sweeping algorithms. So in this case, he used the combine the two core tensors as one, and then this updated this combined tensor updated by using gradient descent optimization. After that, they decompose this tensor by using singular value decomposition. And the optimized core tensor is shifted right, and then left side. This is the one sweep of algorithms. Okay, so this is the starting point I want to consider. Then in our motivation, we want to extend these algorithms for more and more different tensor network architecture and other loss functions, and also develop more stable and more efficient optimization algorithms. Okay, so I will show the three things later. The first one is I will show that this optimization can be used, can be solved by the alternating list squares. So this is considering optimization functions, objective functions, and the bottoms are graphical notations. And then we want to optimize this red core tensors. So in this case, we can consider such objective function. So this is a totally linear. These are linear. So bottom this networks are linear operator. Then this can be optimized by the least squares. This is the algorithm. So we can optimize A1 and then A2 and then AL. So this can be optimized by such formulations. Okay, this is one first result of so to optimize that this optimization problem by using alternating least squares. The red line is a gradient descent using QR decomposition. This line is a gradient descent with sub-singular value decomposition, and finally this blue line is alternating least squares algorithms with QR decomposition. So much faster than gradient descent. Also, good thing is alternative least squares has no hyperparameter like learning rate. And also we can guarantee the monotonically non-increasing. Okay, so then this is ongoing work, but this idea can be straightforwardly extended to any tensor network models like CP, TT decomposition, tensor ring decomposition, hierarchical Tucker, Peps and Miller, something like this. But we have still challenges. Sometimes we are faced about the problem of vanishing gradient, searching best order of contraction, and efficient optimization methods like stochastic or some randomizer methods. Okay, so next we consider the different direction. The second direction is we want to extend the any loss functions minimization. So basically, the alternate least squares is for L2 loss. However, we want to use other loss function. So how to exploit the least square solver for other loss function? In this, for this problem, I introduced two approaches to the plug and play approach. The one is the majorization minimization. Another one is ADMM. In this approach, can be written in like this. So first, we have the many candidates of the tensor network structures, and also we have many candidates of loss functions. And so the important point is this. So right side and left side are totally separated. And the right side depends on only loss function, this process. The left process only depends on the tensor network structures. Then we can freely combine any tensor networks and any loss functions. This is important structure to design the algorithms. So first, I will show about the majorization minimization algorithm. This is very fundamental technique for optimization. First, we consider to minimize a function fx, and then we consider the surrogate function gx. And so surrogate function should upper bound the original loss function like this. And we iteratively minimize function gx and update this surrogate function. And it's like EM algorithm. And also this maybe, okay. Saying the key point here is we can guarantee the monotonically non-increasing property by using MM algorithm. It's the one example of applying the MM algorithm for the logistic regression. So here we consider loss function, and we employ the logistic loss. And this can be majorized by using Fourier gamma augmentation. Then the optimization problem is modified by like this. And in this case, we can use alternating least squares algorithm for this. So the process become like this. We initialize the tensor WT, and then we update this parameter omega and kappa. Then we can use least square solver. So we can program and play any tensor network structures here. And then we iteratively solve and apply the LS solvers. Then we can optimize the different loss function. This is the result of the application of majorization minimization ALS to the logistic regression problem. This is also same. So our algorithm is much faster than gradient descent. We have no hyperparameter, and also we can guarantee the monotonic non-increasing. Okay, so second approach of plug and play is ADMM. ADMM is the method to solve this above problem, and we consider three-step algorithms like this. It also directly apply tensor network optimization. It's a little bit complicated, so I will not explain in detail. But the blue line is can be minimized by alternating least squares, and the bottom two lines are some specific process for some specific loss functions. So then we can consider, so the different loss function can also be optimized by using least square solver. So the left side is we can choose any network structures and also any loss functions by using these algorithms. So the bottom result is the result of using so we can choose a combination of CPD and L1 loss, Taka decomposition, L1 loss, and K divergence, tensor ring decomposition, and with L1 loss and K divergence. So we can choose any combinations. This is the point. Okay, so let's close my presentation. This is summary. So majorization, minimization, and ADMM can be used for tensor learning. And the point here is we can exploit any least square solver. It's not for only the tensor network. Also, we can use non-negative matrix factorization, non-detective tensor factorization, the smooth component analysis, and many types of least square solver as a plug and play manner in the left side. And the right side, we can optimize many loss functions. But in this research, I just tried the logistic loss and L1 loss scale divergence. Maybe many other loss functions can be considered. Maybe in the near future works, I think. Okay, now we can apply the many tensor networks for many signal processing and machine learning tasks using in plug and play manner. So let's time to try tensor networks in various applications. Okay, thank you very much.
Thanks for Professor Yokota for the interesting talk. Are there any questions?
Thanks for the interesting talk. I'm wondering, why do you use the least squares? Because for me, if I want to combine multiple tensor networks together in a model, maybe a more straightforward way is just use gradient descent. Use the backpropagation to backprop the gradient to all the tensor networks, and for updating the core tensors. So is there some deeper motivation of your work?
Thank you very much. So one of the big reason is so gradient descent is slow, and we needed to optimize, tune the hyperparameters, and if we fail the setup of learning rate, then we fail. So the ALS is more stable. This is one reason, and also gradient descent sometimes have the vanishing gradient problem, and because tensor network have many tensors, and when tensors are to multiplied many times, and sometimes the tensor is have small norm, so it becomes too easily to be zero. So we want to avoid such situations.
Yes, thank you very much. So you mean in your methods you can avoid this kind of gradient vanishing?
But I think cannot avoid it totally, but a little bit better than gradient descent. Yeah. This is my
thank you.
Intuition. Thank you.
Okay.
Yeah, thank you for the wonderful talk. So, and you did a lot of fundamental tensor network research, and you said it's time to apply to various applications in machine learning and signal processing. So do you have any idea what kind of application in machine learning or signal processing it has potential future for applied tensor network?
It's a very big point. I want to know the good application. But the first one is I'm considering about the image reconstruction in signal processing, and also I want to try about the so I want to try many network structures for the machine learning problems, and consider some deep learning, comparing the deep learning models. And also important perspective is that using the compression, model compression in deep learning. Thank you.
Yeah, thanks.
Thank you very much.
Okay, due to the time limit, that's the end of this week. Thanks, Professor Yokota, again for this
Thank you
interesting
very much.
Thank you. First of all, I would like to thank Chibin for inviting me to RIKEN AIP and for the opportunity to meet every new friend here. So actually, this is my first time here. So I guess that's a very good opportunity to seek for some collaborations in the future. And just mention that I lead a very small group in PolyU, and the name is Lumen. Lumen means the low resource, ubiquitous, model efficiency, edge intelligence, and novel applications. So our goal is to investigate fundamental research problems to enable efficient utilization of edge AI. So that means we will focus on learning and modeling with limited resources in terms of data and constrained computing capability, and as well as exploring their derivative applications on wider spectrums. So now we have some open positions in the next year. So we have for PhD students and 2 postdocs. So if you have some students you can recommend, okay? Thank you. So, so that's our research framework, and today I would like to focus on the narrow topic, the ratial learning, and especially for its fine-grained analysis. So the target of the ratial learning is actually training a mapping function from the input space to a shared semantic space, and based on the shared semantics, we can transfer the mapping function into infer adding real examples from the unseen domains. So taking the image as an example, the ratial learning is to train a visual to semantics mapping function based on the seen domains, and we can use this trained mapping function to infer unseen classes. So in ratial learning, we normally have 4 tasks. The first one is the standard, most standard ratial learning, meaning that we only infer unseen classes during testing. And secondly, the generalized ratial learning, meaning that we have to infer both seen and unseen classes. So in the generalized setting, because the mapping function is only trained on the seen domains, so the mapping function can naturally bias to the seen domains, right? So that's we call it as a domain shift problem. And then, based on the generalized setting, we can also infer multiple classes in just one sample, which we call it as the multi-label ratial learning. And in recent years, we can further decompose the samples into 2 parts: the states and the objects, and then we can mix up the state and the object to form and to recognize any novel combination of these states and objects. So that is a compositional ratial learning. So, so this is the brief formulation of ratial learning, and there are 4 tasks. And in the visual to semantic mapping function, the semantics are another very important input. So here we normally have 3 kinds of semantics to bridge the seen and unseen domains. The first one, very simple one, the attributes. The attribute is usually the most usually defined by the expert, which meaning that the intensity, usually the intensity of the given concept. It can be binary or can be continuous values. And secondly, we can also use some words and some sentences to describe the concept, right? And then we can use this word embedding or sentence embedding to present this class. So that is the semantics, textual descriptions. And meanwhile, in recent years, we can also use some pre-trained visual language models, such as Eclipse and some of their variants to do the ratial learning, which I guess is the very natural value to semantics mapping function, right? So we can use it directly to do the rational reasoning. So the rational learning is a good way to enable generalization with the limited data and the limited computing capabilities, which I think is a very promising way in the future. And we can apply the rational learning to many real applications in multiple domains, and we believe that more and more applications can benefit from the rational learning in the future. So now challenges. The first challenge in rational learning is the domain bias problem, which is the most common challenge in rational learning. Actually, we already mentioned that problem in the generalized setting, right? And the second one is the hardness. The hardness means that a few clusters inside the mapped feature space may dominate the most samples. So the hardness is not a unique challenge in rational learning, and it happens in many classification problems and also many clustering problems, right? And the lightweight requirement is another critical problem, especially for running the AI on the edge devices, right? Like the smartphone, like smartwatch, and something like that. So to address these challenges, we have systematically investigated the value to semantics mapping function, and we have provided three kinds of solutions. The first one is the feature decomposition, and the second one, the semantic expansion and the cross-modal interaction. And so the first one, for the feature decomposition, we focus on the input feature space, and normally the value feature space. Here, we decompose these features to more fine-grained concepts so that we can better align the mapping function. For the semantics expansion, it means that we will use all available resources to improve the richness and the diversity of the semantics. And meanwhile, the cross-modal interaction focuses on how we can fuse the cross-modal information in a better way. And lastly, I will also very briefly show some real examples of our application. So first, for the feature decomposition, we cover four works. They decompose from the low-level features to middle-level features and to high-level features. So here, you may understand the level. You may understand the level as the depth of models, like the different layers in the deep neural networks. And normally, the shallow layers are usually more figurative concepts, and the deep layers are more abstract concepts, right? So that's a very standard observation in CNN structures, right? And for the firstly, for the low-level decomposition, we focus on the basic elements of the samples. Specifically, we first localize and decompose some key points or key parts in a sample, and then based on these elements, we can reorganize the objects into a graph structure, which we call the sample level graph. And by propagating and fusing the information among these graph nodes, we can fully make use of mutual relationship and the substructure information of these fine-grained elements, so that these elements can better align with their semantics, right? Because the semantics are usually more fine-grained descriptions. So it can be correspond to some specific regions in an image, right? So this work is the first attempt to reformulate the rational learning problem to a graph to semantics mapping task. And we obtained the SOTA performance in 2023. So we can see from the realization that our method can have more separated sample distributions, and meanwhile, their margins are obviously larger, right? So these samples can be better divided. And next, we talk about the middle-level decomposition. So in this part, we have a very interesting observation that different layers or different channels may have quite different sensitivities to unique concepts. And these concepts can further correspond to specific semantics, right? So that is for the value to semantics mapping function. For example, in the first work, we found that the deep layers in networks mainly focus on large objects, because deep features are usually more abstract and more globally informative. And in contrast, the shallow layers are more sensitive to the small objects. So we can use such multi-scalar information to improve their performance. So that is the core idea for the first work. And in a different way, the second work uses the channel class correlation. For example, we can reasonably guess the channel response of the concept garden if we know the responses of the water and the tree, right? Because the concept of garden usually covers the concept of water and the tree, right? So that is the core idea for the second work. So that's a pipeline for the first work. We deal with deep layers, middle layers, and shallow layers separately to improve the visual semantics mapping. And yeah, you can see that our method can have a better response to the fine-grained concept, right? So here the sunset, the grass, right? The grass, we can highlight the portions of the grass, and also the clouds, right? It's very clear, right? The clouds. So that is our result. And then that is the pipeline for the second work. And regardless of the layer depths, we shuffle and we organize all these channels. And afterwards, we can explore their channel class correlation. And the results are similar, right? The results are similar. We can better capture the concepts on the attention maps and cover more fine-grained regions. Last, for the high-level decomposition, we can decompose the mapping function directly. We call it as network refactoring. So here, our target here is to maximize the representation ability of the network, as well as account for the on-device friendly deployment. So that is also our core goals of our lab, right? On-device deployment. So for that purpose, we first refactor the deep networks into a set of simple linear networks so that we can reduce the overhead from nonlinear complexity to the linear complexity, or at least the quasi-linear complexity. So that is the first part. And meanwhile, we further design a simple wise indicator to select only a subset of linear networks for one inference, right? So thereby we can reduce the inference time. And for this problem, we can reformulate it to a quadratic programming problem. And this problem can be solved effectively using existing and well-implemented solvers. To further improve the representation ability, we also force the low-rank structures on the interclass samples and force the optionality on the interclass samples. So that makes the feature have the largest margins for different classes. So by combining this lightweight design together, our method can obtain comparable or even higher, better results against most deep models. So more importantly, our model can be deployed on very tiny devices like the Raspberry Pi. So here you can see this figure. Our method can obtain comparable and better performance against most deep models in the rationality task. Now, from the input space, we go into the semantic space, okay? So for the semantic space, we consider the expansion of this space. So for here, we also cover 4 works. They use the generative models, prompts, large language models, and multimodal models to enrich the semantics, and therefore can make the semantic space more powerful. So first, we use a variational autoencoder to generate new auxiliary semantic features, and then we train the new and the original semantics together to approximate to the various manifold. So such an approximation can better align the vector space and the semantic space, so we can improve the generalization ability of the rational learning models. So that's our results, and we can see it is much better than other methods. Next, the prompts are another way to bring about the new stuff, right? To bring about new stuff in addition to the VAE. So in the second work, we use the trainable soft prompts to expand the semantics, and we further minimize the divergence in the pair space. So in this aspect, the idea is somewhat similar to the manifold involves that in the first work. So however, this work also involves cross-modal interaction, and we will continue to discuss this work later in the next section. So lastly, we can also use the large language models or multi-model models as a knowledge engine to generate site information. So such site information is usually more meaningful and more clear defined knowledges rather than the VAE or than the prompts, right? So that's another kind of direction by using the large language models to generate some site information to help the recognition. So here we first have the one-turn site information to implement the skeleton-based zero-shot human action recognition. So here the one-turn means that we only have one query to ask the large language models, like what would an action look like? So the large language model can answer some fine-grained descriptions, and we can use these descriptions to achieve more fine-grained recognition. So here we show a queried example of the action like the drink water, right? It shows how each part of a human should look like when drinking the water. So we can see this set information can provide more fine-grained and more accurate descriptions. So it is much more helpful for the accurate recognition. And besides the one-turn set information, we can also query multiple trials in a contextual way, meaning that we could decompose an action into different phases. And one phase can evolve to another in a given context, right? So for example, when drinking the water, you need to first pick up the cup, right? Pick up the cup, and then you can lift the cup with your hand, right? And then finally tilt your head back and drink, right? So there are three phases to complete the action, drink water. So we call it as the involving representation, so which can bring about more fine-grained information for the rational learning recognition. So following some results, we have three phases, and each phase, one phase can evolve to another for a given action, right? So now we have finished the input space and the semantic space, and lastly, we cover three works for the cross-modal interaction. So firstly, we continue this CVPR work in the semantic expansion and further introduce the decompose and the fusion strategy. So different from other works that decompose the various features for the states and objects in the compositional rational learning, we instead decompose the semantics because we believe that the semantics are usually of much lower complexity, right? So which can be decomposed easily and preciously. So then we can fuse this decomposed state and object features with the original visual features for better interaction. So that is the core idea for this paper. And then this is the result, much better than the competitors. Next, in the second work, we noted that the coarse-grained features and the fine-grained features can also benefit from each other, right? The coarse-grained features are usually focused on global features, right? Like the shapes, like the locations, and something like that, right? And the fine-grained features normally focus on some specific regions, very tiny parts, right? Like different parts of humans. So the coarse-grained features can help the classifier or help the neural networks to localize to the core regions, right? And then the fine-grained features can help the networks to find some subtle differences of different classes, right? So based on this idea, in this work, we maintain two kinds of expert networks, one for the coarse-grained features and the one for the fine-grained features. So we can distill these two experts so that they can learn from each other for better representations. And this is the result. We can see that the coarse-grained expert and the fine-grained expert can both achieve accurate recognition from distilled knowledge from each other, right? The coarse-grained features can guide the fine-grained expert to find the regions, and the fine-grained expert can, in return, help the coarse-grained features to focus more subtle regions, right? So there's a mutual improvement. Lastly, we can also create a group of prompts to interact and fuse with fine-grained value features. And more importantly, we can force these non-verbal prompts to minimize the divergence with the targeted semantics so that the visual to semantic mapping function can be more accurate. So following the results. Lastly, I would like to very briefly show three related applications. First, for the resource efficient human action analysis, we have integrated 4 works into one framework, and which can firstly utilize the Wi-Fi signals to estimate human pose, and then followed up with highly efficient skeleton-based human action recognition techniques to analyze various kinds of human activities, such as the rehabilitation assessment, fall detection, abnormal behavior detection, sports and training analysis, and so on, right? So that is for the smart mobility and also for the healthcare, many applications. Here, I would like to highlight our Wi-Fi signal-based human pose estimation model, and which is a very challenging task. We use the Wi-Fi devices to capture and analyze human activities. There is no cameras, no any more sensors, just Wi-Fi devices. So our solution can be more privacy protected. Meanwhile, such recognition and analysis only happens on the edge devices, so which can guarantee the efficiency. So we have already released some preliminary results, and in the future, we plan to establish a comprehensive data set covering 3 modalities, including the Wi-Fi signals, skeletons, and real human images to standardize this application. So which means that in the training phase or in the modeling phase, we only use, we use 3 modalities like Wi-Fi, skeleton, and nature human images, while in the inference, we only use the Wi-Fi signals. So that relies on a very accurate and a very robust alignment between these modalities, right? So that's a nature extension for the rational learning. Secondly, for the human group analysis, we also have some works that covers human mobility analysis, like the traffic flow, vehicles, pedestrians, populations, human positions, and so on. So in the future, by using the AGI techniques, I believe that we can have more insight in this field. We also have some application for the cybersecurity. For example, our proposed open set recognition techniques are already adopted by the China Southern Power Grid and the Guangdong government. So the open set is a special case of virtual learning. So this application is a natural extension of our work. Meanwhile, our PassNet has also been partially adopted by the Hong Kong local company, the Moon Lab, which is actually a Web3 company. So in their enterprise-grade solutions to provide fast storing and managing on-device utilization. And lastly, because I am also jointly appointed in the Department of Land Surveying and Geoinformatics, so I also have a new proposal for the topic on-edge utility management, like the management of energy related public utilities. Here, our target is to fully utilize the HAI techniques to better manage public utilities for better well-being. So this will be a future work in our application. Last, I would like to conclude my talk with our recently released survey. So in this survey, we have systematically summarized the most recent research on virtual learning, and especially on the fine-grained techniques, covering algorithms, different designs, benchmarks, open source groups, and also some suggestions of potential directions. So if you have interest, you can find our survey. So this is some related outputs in this direction. And lastly, you can scan the QR code for more information for the Lumen Lab at Purdue. Thank you.
Thanks, Professor Guo, for the wonderful talk. Are there any questions? Okay, can I ask a question?
Yeah.
So I'm interested in your work of the ParsNet. So in the ParsNet, you decompose the function into the summation of several linear functions.
Yeah.
How do you guarantee the performance only using linear functions?
Actually, for the virtual learning, we normally focus on we focus more on the semantics. The semantics are usually more, much more simple representations, right? So that is the first reason. And the second reason is that we will also use some pre-trained CNN extractors to extract the images. And then that's the second step. The third step is that we will combine the different types of linear networks. And for that set of linear networks, each networks can correspond to a specific, maybe only one specific descriptions in the semantics. So we combine these descriptions together, meaning that we combine different types of linear networks together to guarantee the performance.
I see.
Yeah.
Thanks. Are there any other questions?
We decompose the feature decomposed as many semantics. So how in practice, how to determine the number of semantics, like pose and some kind of a structure or gesture, pose or something. So how to decide how many semantic sub-functions?
Sub-function, okay. So usually this is, we just by trying different set of neural networks. Yeah, we just try different numbers of neural networks. Yeah. So this is actually just a manual trial, and then we can get some feedbacks from the result, and then adjust the number, and then also continue this work. Yeah.
Okay. Yeah, like parameters to
yes, very similar. Yeah, very similar.
Okay, if there's no more questions, let's thank Professor Guo again for his wonderful talk.
Thank you.
Good afternoon, everyone. First of all, I would like to give my great thanks to Professor Qibin Zhao and AIP for inviting me to present my work in RIKEN, and also give me so many opportunity to know many of the talents here. And my talk is some developments in density ratio estimation for statistical inference. The quantified diffusion Schrödinger bridge for density ratio estimation. These are the co-authors from South China University and of Technology and Columbia University. And the paper was published in ICML 2025. This is the brief introduction of my working experience. At present, I am a faculty of School of Electronics and Information Engineering in SCAT. Before that, I worked in Xiamen University, and I have been visiting scholar in Columbia University and University of Waterloo. And my research interests are machine learning and pattern recognition, statistical inference, PDE and SDE modeling and their applications. So this is the contents of my talk. My topic would go to a little bit fundamental. Let's get to the background of density ratio estimation challenges. In many scenarios, we have to compare or compute two random variables. For example, x0 and x1. Particularly in the case of mutual information calculation, density estimation, and KL divergence estimation. In that case, we usually have to calculate the deal with the relationship between two random variables. Particularly for diffusion model and normalizing flows, we usually transform one random variable to another. We would transform the data of random variable to the some node distribution called base distribution. Okay. In that case, we had to compute the density ratio estimation given in equation 1, P1, and P0. For this computation, we usually come across the challenge of density Chasson problem. For example, there's P0 is a block Gaussian distribution of 1 and 0, and P1 is the very steep Gaussian distribution with sigma of one exponent of -1 to minus square. Let's see the result of Rx denoted in black light. That would go very steep. That would cause the problem. Usually, some words will deal with the problem with TRE method. They decomposes the direct ratio into m small steps, while linear interpolation, denoted by equation 2, will be increased from 0 to 1. the density ratio is then expressed in equation 3. Then Rx can be expressed in the products of intermediate density ratios. If we let m go to infinity, that would have we would have the version of DRE infinity. Then we have the continuous interpolance of equation 4. Then the log ratio is expressed as a time integral denoted by equation 5. You can easily solve log. We can use a log transformation in this case. Then the results will come from a computation of definite integral, where partial t log pt denotes the time score. That is different to the spatial score. This is time score. Then how we construct the energy functions to calculate, to approximate partial t log pt. We use the equation 6 as an energy function to calculate S theta. S theta usually is the neural network. In that case, we choose PT based uniform distribution, and lambda t only a weighting function. Sometimes it depends on the variance of partial t log pt. Then we have the estimation of equation 7 log Rx. Log Rx and is equal to the integral integrated from 1 to 0 to 1 of S theta. Then if we can construct that neural network, then we would have the ratio Rx. Let's talk about the limitations of these existing solutions. There are key failure models of prior works we just talked about. The first one is support transient. Usually, we will have ill-defined ratios when support Q0 and the intersection of support Q0 and Q1 is really, very small. Sometimes it goes to empty. Then it would cause unstable and sensitive training and estimation, with P1 times by P0. The second is boundary instability. Time scores expectation of partial t log Qt usually diverge as t goes to 1 from the left side. We would have a theorem to prove that. That would cause unstable training and estimation as well. The third, computational inefficiency. Usually, people would use numerical ODE solvers to solve this problem, but usually it would cause computationally extensive. The gap is no methods simultaneously to address support coverage, boundary stability, and efficiency. So we are going to give our method here. We firstly denote the previous words as including the TRE and DRE infinity to deterministic interponents, defined as the equation 8. We denote that interponents as a linear connection between x0 and x1. For this, alpha t and beta t belong to a C2 family of functions. It satisfies the two the boundary conditions and coupling conditions. For the boundary conditions, alpha 0 is equal to beta 1 is equal to 1, and alpha 1 is equal to beta 0 is equal to 0. Challenges comes DIE with the previous words, we denote it as deterministic interponents suffer from support chain problem, where minimal overlap between the intersection of this support leads to ill-defined ratios. Let's come to our solution. The solution is DBI, diffusion bridge interponents. We ingest Brownian bridge stochasticity and expand the support in as denoted in 9, in equation 9. Beta T is the Brownian bridge. Then after reparameterization check, we rewrite the equation into 10. It's 10. Here we show the trajectory sets among DBI. This is DBI. In the following context, we will give DDBI and DSBI. The first one is DI, the previous works. The latter ones are our improvement. We can see we have a broader trajectory set. We would give that result by some theorem and corollary. Okay. Then the first is DDBI. The boundary time scores diverge for DBI and DI. For the XT, we have when the time t belongs to 0 and to 1, belong to the set of 0 and 1, we have the result of 11. The expectation of partial t log qt is greater than some value. That value, L is the Lipschitz constant of partial t log qt. Moreover, if the L Lipschitz constant of partial t log qt is smaller than 1, this lower bound diverges to infinity. It is denoted in equation 12. You can see the second equation. It diverges. Since it's the lower bound, it diverges. Then the left side would diverge as well. How to deal with that problem? We use a strategy of modification. We modify the endpoints with Gaussian noise by the way of 13, where we give a Z, epsilon Gaussian noise. Then we use the DDBI denoted in 14 and equivalent to equation 15. We write that the interponents into equation 15. We see the epsilon is from here, epsilon. Then this is the DDBI. Okay, for the DDBI, we have the uniform approximation of density ratio Rx. R prime is the estimated value. R is the true value. It approximates to R as epsilon goes to to 0. So for the following proposition of 16, we can ensure the expectation of partial t log qt is bounded. It's bounded by this value. So let's go further, a little further, to reduce the estimation error and improve the efficiency. We are going to give a DSBI, the quantified Schrödinger bridge interponents. We give another interponent. We treat this problem as a transport problem. as an entropically regularized optimal transport problem denoted in 70. We give a new energy function regularized by entropy. Here, pi from Q0 pi to Q1 pi is the set of all probability paths with the marginals Q0 pi and Q1 pi, and h of pi is the entropy of pi. So we consider all the sets, all the trajectory. We would like to find an optimal trajectory to transform from x0 to x1. Then we together with the OTR method, optimal transport arrangement, particular for single-horn algorithm, we get a new DSBI, the quantified Schrödinger bridge interponents denoted in equation 18 by solving the previous energy function. Then we have another result. The DSBI have a tighter upper bound epsilon than DDBI, the previous method we gave. So DSBI seems to be much more favorable. So we give that result by theorem 2. So we have another interponent DSBI, the quantified Schrödinger bridge interponent. Interponents, these are all interponents. So let's get to the summary of the talk. For the conclusion of the D3 RE, it means DRE, density ratio estimation, we built a unified framework to address both density traction and support trends, enabling uniformly approximated density ratio estimation. We gave two modules, DDBI and DSBI. For DDBI, it expands support and stabilizes boundary scores via diffusion bridge and gradient descent. The second, DSBI, it improves efficiency and accuracy by solving the Schrödinger bridge using OTR. And we also have extensive experiments to validate the framework, such as the case of mutual information estimation and density estimation. As we know that density estimation has a lot to do with generated model. If we have the underlying or potential distribution of the data, we can generate as many data as we wish. So this comes to the summary of the method to comparison and of all the interponents in this work. Okay, we can solve the DSBI, DBI, DI are the previous methods. We just denoted this method to be DI, and DBI, DDBI, DSBI are our method, our improvement. We can show that it has some favorable performance, including the stability and efficiency. So we can show the experiments on density estimation on synthetic for density estimation. The first line are the data. The second line are the baseline. The previous works we denoted as DI, and the third and the fourth and the fifth are our improvement. We can show that we have a better results in density estimation on this synthetic image. And also we have quantified results, and we saw our our performance is better. And for mutual information estimation, I just told at the beginning, we can solve the distribution with density transient and support transient problems. For this, DRE infinity is regarded as the baseline. We can solve the baseline by the dash. This is the baseline, the yellow baseline, and the blue one baseline, yellow, blue are all the baselines, and the red and green, red and green are our improvements. And this is the other operations. We can see that our methods have less number of function estimation than the other methods, but with acceptable, reasonable performance of stability. Future works. Let's come to talk about the future works. For this talks, I mainly talk about the interponents. We give some interponents to interpolate between random variables. For there is the weighting functions alpha t and beta t. We know that this is the previous choice of alpha t and beta t, including VE, VP linear form cosine. We can see their difference. In the result, in the experimental result, in this figure. All we want to do is to calculate log Rx. Okay, so we can get to the point to raise a question: is there any optimal interponents for minimizing estimation error? The core idea is we also calculate the error between the true and the estimated DRE ratio. We calculate the expectation. This error is bounded by this inequality. We can, for the upper bound of the error, it can be decomposed into two terms: the path dependence and the path independent and the path dependent term, where VA is expressed in this way. You can see there are alpha t and beta t. So alpha t and beta t are very crucial to construct the trajectory between two random variables. Also, for future work, we have used Gaussian process to control alpha t. We may have better results. This is our ongoing work in the future, and this will come to the reference of the work. And the first one are the paper of the speech in ICML, and these our teams. Their team. Thank you very much. Thank you for all your attention. Thank you so much.
Thank you so much for Professor Zeng's great talk. Do we have any questions or comments?
Yeah, thank you very much for the interesting talk. I'm not sure I'm really follow on the every point because it's so hard.
Sorry, I didn't speak so clearly.
No. So I have a general question about the connection to tensor networks. Could you give more intuitive maybe comments or your idea? In your introduced work, say some possible points we can connect your works with tensor networks.
Did you mean the neural networks?
No, tensor networks.
Tensor network.
Yeah.
Okay.
So
That is a good question. This is what the reason of I come to RIKEN. I would like to learn from AIP how to use tensor, the perspective of tensor to describe this this problem. I think for my method, I usually use the method of calculus, the method of probability, and it lacks the method of descript method. For example, the tensor, the matrix. Maybe is there any? If we can we calculate the eigenvalue or eigenvectors? Is the eigenvalues meaningful to the interponents? I am not sure. I don't know. I want to know so much about it. For in my opinion, I think I consider so much about the random variables to construct how to construct the trajectory from one random variable to another. Then we can shift the distribution from one to another. We use diffusion model. We transform the data of the distribution of data to the basic distribution, so-called Gaussian distribution. Can we do that? Can we do that for this one? If P1 and P0 are all unknown distribution, is there some trajectory between them? Is there the trajectory between them are optimal in the sense of energy causing and time? I don't know. There's a workmate in my university. He published a paper in a pure mathematics. Is there a space to contain all these density functions, better space? He proposed, no, he just gave some results in the space of Tatsuya space. Tatsuya space. We can use some energy, we can use we have to calculate some geodesic life of the energy function built on that space. Okay, this is all I want to share. Okay, is there any further questions? Sorry.
Yes, thank you very much.
Thanks for the talk. So in the original form in equation 1, there's only P1 and P0.
Yeah.
So maybe you can do sampling in using one path. But in your form, you use multiple, like the bridges. But what about the sampling procedure of your method?
Sampling. We can use give sampling method if we have the density estimation. If we have calculated Rx, then if P0 is no, then if we have P1. P1 is the distribution of data. Then we can do sampling by many of traditional methods.
I mean the sampling complexity. For example, in the original form, you can from P0 to P1. But in your method, maybe there's multiple T. So what about the sampling time?
Okay.
Is it longer than the original one?
You're raising a very good questions. For this one, if we want to sample this one or this one, anyone is okay, P1 or P0, we have to deal with every point. So for every point, we calculate that. If we have trained a neural network S, then for every x, we can do sampling, fx. If for x is an image of maybe m by n, then this complexity is m by n for that equation. But And we have trained, after we have trained that neural network. So for this neural network, we have to do integral. So integral, we can use the traditional way of ODE solver, or the definition, the definition to calculate a definite integral. Yeah.
Okay, thank you.
Okay. Thank you.
Let's thank Professor Zeng again.
Okay.
And,
Okay. Thank you so much.
Thank you, Mingwan, for the introduction. Also, thank you, Chivin, for inviting me. I'm very happy being here and meeting old friends. I would like also to congratulate the Tensor learning team for the impressive achievement in the last years. My talk today is about the importance of low-dimensional models for machine learning, but especially in the case when we have incomplete data samples or data samples that are given in a compressed format. This is a collaboration work with the Tensor learning team in RIKEN AIP, where I'm visiting scientist. Let me give you some quick introduction of myself. I'm from Argentina, South America, very far, far away from here. I have a position of adjunct professor at the University of Buenos Aires in the engineering faculty in Buenos Aires City, and I'm full-time researcher at the Radioastronomy Institute of Argentina. This is part of CONICET. CONICET is the National Council of Research in Argentina. It's like RIKEN, but at Argentinian level. Okay, this is the roadmap of the talk. At the beginning, I will introduce and give a definition of what are low-dimensional models and what are their roles in machine learning. Then I will introduce a problem that we usually have in machine learning application, that is trying to learn to train a classifier, but with incomplete data samples or compressed data samples. I will describe some classical methods that people used to use. And then I will introduce our approach. This was a work presented at a workshop in the CVPR conference in 2021. And I will discuss some theoretical and experimental results of that paper, and finally, some general conclusions. Okay, so let's start on what is a low-dimensional model. We can take this definition. A low-dimensional model is a simplified representation of a complex mathematical object using fewer variables or fewer degrees of freedom than the original high-dimensional object. For example, if we consider a high-dimensional vector space, the simplest low-dimensional model is considering a linear subspace. This is the case when, for example, we have a data set and we applied principal component analysis or SVD on this data set, and we obtain a low-dimensional subspace, a linear subspace. Another example of low-dimensional model is considering union of linear subspaces. And this is exactly the case of the compressed sensing theory, when we consider that our data samples can be expressed as a sparse code using some dictionary. I will explain more about this because we use this low-dimensional model in our paper. But we have also other methods to reduce dimensionality. In particular, we have some nonlinear methods. One is the use of autoencoders, because in an autoencoder, we have a latent representation of the input data in the middle of this architecture here. And we can interpret also low-dimensional model as a manifold. A manifold is a subset of points in our space with the property that locally it behaves as a linear space. Okay, but we also have low-dimensional models for tensor space, not only for vector spaces. All of you know very well what is a tensor. It's a generalization of vectors and matrices to higher number of dimensions. And low-dimensional model for these multidimensional objects usually takes the form of a low-rank tensor decomposition. This is a classical example, the Tucker model, for which the high-order SVD is a particular case. And in particular, in this model, what we do is to find linear subspaces for each of the modes of a tensor. And we use this linear subspace approximation in all the modes simultaneously. More examples of tensor decompositions are, for example, tensor networks. Here I show in particular one architecture, which is the tensor train. And this figure is taken from a paper that used the tensor train to compress two-dimensional images. As Professor Chivin explained before in his talk, we can use tensorization of images to construct a large dimensional tensor. And in that new object, multidimensional object, is very useful to consider tensor network because we can capture the structure of an image in this higher dimensional space. In fact, what we do when applying this tensor train to the tensorized version of an image is to capture the linear subspace related to each multi-resolution level of an image. And there are many, many different tensor decompositions. I mentioned also here the CanDecom parafab decomposition, which is the sum of rank 1 tensors. And also I mentioned the sparse Tucker decomposition. It's a tensor decomposition that we developed with Professor Shichowski a long time ago. And we were able to generalize the theory of compressed sensing to multidimensional signals. Okay, so now that we have defined what a low-dimensional model is, let me discuss briefly what are the roles of low-dimensional models in machine learning. In a machine learning problem, in supervised learning, for example, we have some predictive model, for example, a neural network, and we have some input data that we feed into the neural network. In the predictive side, it is very well known that low-dimensional models plays a significant role. There is this Occam-Razor principle that said that the simplest explanation that fit the data is usually the best. This is very well known, and some ways to impose this low dimensionality could be to use regularization, sparsity constraints, and so on. And let me mention one interesting paper that came out this year by Sun and Nielsen. They study the space of parameters in a deep learning architecture, which is a very high dimensional parameter space. And they found that when you train the parameters, you train the neural network, the solution lies on a low dimensional manifold. And that's why deep neural networks are very good at generalization. But in this talk, I will focus on the low dimensional model for the data representation. And let me show you how we can solve an important problem in machine learning using this low dimensional model. We want to solve the supervised learning problem when the input samples are incomplete or are given in some compressed format. There are many examples in machine learning when we have this kind of incomplete data sets. For example, in recommender systems, here we have some movies and we have some users, and not all the users have an opinion on every movie, so we have incomplete information in this matrix. The same things happens with medical data set. We cannot perform all the medical tests to every patient. We have some occlusion problem in computer vision, for example, in self-driving cars. And in other examples, we have the measurement that are given in a compressed format. This is the case of magnetic resonance imaging or tomography, remote sensing, microscopy. So let me illustrate this problem. This is a toy example that is represented only in 2-dimensional, but it's very high dimensional, the problem. Suppose we have two classes, the numbers 3 and numbers 8, and we want to train a classifier to separate these two classes. Let's consider a linear classifier. We can do that if we have the complete version of the input samples, but in reality, what we have sometimes are incomplete versions of all these data points. So we don't have the location of each point in the high dimensional space, so it's difficult to train. So the goal is to train a good classifier, but using only the incomplete data samples. The classical approach is a sequential approach. In a first step, we just complete the missing features, the missing pixels, for example, in images. And once we have complete all the information, we just train the classifier on these completed data samples. This is the representation of the previous examples. We have incomplete version of each data sample. We complete using some algorithm, some image in painting or image completion algorithm. So we obtain some complete version of the original incomplete data samples. But what we observe here is that we have a problem. Once we complete the same data samples that I showed you before, now we cannot train a good classifier on these data samples. So the first lesson we learned here, if we consider, for example, this case, it could be complete as a 3 or a number 8. The first lesson we learned is that we need to consider, to take into account the class of the incomplete data samples when we try to complete it. So this is kind of supervised completing algorithm. And this can be done, and I will show some results, but we propose a different approach. Our approach, this was presented in this workshop in CVPR. This is our approach. We have our machine learning problem. We have a neural network that we want to train, and we have some incomplete version of the input data samples. We can express these incomplete measurements or compress versions of the data samples as the product of a matrix, observation matrix, by the original data samples. What we do is to assume some low-dimensional data model for the input data set. In particular, I use the sparse coding model because it's very powerful for images, and also is simple to be integrated in a deep neural network architecture. What is a sparse coding? Sparse coding means that each data sample can be represented as the product of a dictionary by a sparse vector. It's a vector of coefficients with most of its entries are 0. In our proposal, instead of doing a sequential approach, which will be first complete the data and then train the classifier, we do it simultaneously. So we train the classifier, the neural network, together with the sparse representation of the observations. How can we do that? Well, we propose a loss function that is function of the network parameter theta and the dictionary D and the sparse code of all the data samples. And this loss is very simple. It has 3 terms. The first term is just the classical loss, the cross entropy, for example. We add a second term that measure the representation error, so it's the data consistency term. And we add a regularization term for sparsity. We try to impose sparsity on the representation. And we develop an algorithm to minimize this loss function. Okay, so we have some interesting theoretical results. The first question we wanted to answer is it possible to train a classifier from incomplete data? Well, for a very simple case, which is only one layer neural network, it's a logistic regression architecture, we prove that if we were able to complete the data samples and train a classifier such that these completed data samples are well separated by a classifier with a good distance from this line, epsilon, if this epsilon is larger than this quantity, this is the weights and the signal, the data sample, restricted to the missing entries. If we are able to verify this condition, then we can guarantee that the original data samples are also well separated. Some quick conclusions or observations about this result. It is not necessary to train a good classifier that the reconstruction is perfect or good reconstruction. We can reconstruct very different, but as long as this condition is satisfied, we can guarantee that the classifier is a good classifier. And also, if we have that the missing entries has a associated weight close to 0, which means that those features are not relevant for the classification, of course, this condition is easy to satisfy because this is exactly 0. Epsilon should be larger than 0. And we also study what is the role of the dimensionality of the low dimensional model. In this case, what is the role of the sparsity of our data representation? And we found this inequality. And basically, we also verified in our experiments with synthetic data that as we have a more sparse representation of our data, this condition is easy to be satisfied. So sparsity is a good thing. As more sparse is our data set, it guarantees that we can train good classifier with not many entries. We made experiments first on synthetic data set, and here we compare with sequential methods. Some of these methods are supervised. We use the class information for completing the missing entries. Some other methods are unsupervised, as you can see here, some unsupervised, some supervised. And we always obtain the better results when we apply our simultaneous method compared to any other sequential method. And we also applied our method to computer vision datasets, simple datasets like MNIST and CIFAR. And we compare with the state-of-the-art method at that time. It was a method proposed in URIPS 2018. And we obtained very good results also. We obtained the best result with our method compared with all these methods. And what is interesting here is that we found that this state-of-the-art method worked very bad when we consider larger images, like the case of CIFAR, with a large amount of missing pixels, like 75% missing pixels. This method works well, but for moderate levels of missing features. We also compare how our method works for different levels of missing entries in training and in testing, and we compare with the baseline. The baseline is to use the same neural network but trained on complete data without using any low-dimensional model for the data input. And here it's very interesting to know that using incomplete data but a low-dimensional data representation allows us to obtain much better accuracy than using the full data without any low-dimensional model using the baseline. And here we had some visual examples of applying our algorithm. Here we show how we complete the missing entries. The first row is the ground truth. It's not available. What we have available is the second row. Here we have random missing pixels. In the figure at the bottom, we have like occlusion. 50% of the area of the image is occluded. And here, what is interesting to show is that we are not reconstructing a very similar number 5, but we still recover the number 5. This is because training simultaneously the data representation and the classification model, we are able to capture the class information of each data input. And finally, the conclusions. Low-dimensional models are fundamental in machine learning, not only in the predictive model side, which is very well known, but also in the data representation side, which was the topic of our work. The sparse coding approach for a low-dimensional model is a very powerful model, especially for natural data. In fact, it is inspired on the visual cortex of human and mammals in general. And because it's a linear model, it's a union of linear subspaces, it's easy to be incorporated into a deep learning architecture as a prior model. And finally, when we approach this problem of supervised learning with incomplete features, our method allows to overcome well-known issues in previous approaches. It allows us to incorporate the label information of the missing features. It's very simple to be implemented because we can still use linear methods like stochastic gradient descent. We can use back propagation. And also sparse coding was more accurate, modeling the values in high-dimensional datasets compared with this state-of-the-art method published in URIPS 2018. So that's all. So thank you very much for the attention, and I'm happy to answer questions.
So much for Professor Caiafa's nice talk. It's very comprehensive and coherent. Do we have any questions, comments? Anything you want to ask?
Thank you for your interesting talk. I consider about your method is two aspects. One aspect is learning classification under the incomplete data. And another one is maybe data recovery by using classification prior, something like this, I think. So you can also recover the data and also learn classifiers. In that sense, so maybe your model can do the many data recovery problems like denoising and super restoration or something like this. So how do you think about the extension for many problems?
Yes, I have not explored yet. In fact, in the paper, we only consider the missing features problem. But when I wrote this in a more general way, because this is a linear transformation. In this case, we can consider also another type. We haven't tested, but I think, or my feeling is that if we consider a good low-dimensional model, we are able to approach other problems too. And also, we can use not only sparse coding, we can use many other low-dimensional models, like autoencoders and many other powerful methods. But we have not explored yet. Maybe it's a good topic for someone else.
Yeah.
I don't know.
Thank you very much.
No, thank you for the questions. Good question.
Any other questions?
Wonderful talk. So in the end, you mentioned the sparse coding could be applied to neural network. So in the end, you mentioned sparse coding.
Yeah, but not for the neural
applied to deep
network.
learning. I'm wondering what kind of applications.
No, I didn't mention in.
Yeah, here.
No. Here is for the data.
Deep learning architecture as a prime model.
Because you can think this sparse coding as a first layer of a neural network.
Yeah.
So in that sense, it's incorporated. It's just an adding a layer. But the way you have to train it is not the classical way, because you have to impose sparsity only on the first layer. That was my message, not in general neural networks for sparse coding. But I have read many papers about regularization in training neural networks using sparsity constraints on the weights. And this is good for avoid overfitting, for example. And it's also good for interpretability of neural networks. Yes.
Yeah.
Did I answer?
Yeah.
Okay.
Thank you.
No, thank you for the question.
Do we have any other questions that you want to discuss with Professor Caiafa?
Thank you for your great talk. Actually, I didn't catch some concept because you connect the supervised learning and sparse coding and also dimension reduction. So by introducing this sparse coding layer, I feel I don't get the concept, but I feel the model is more complicated because you add more layers in the sense of neural network.
Yeah. Yes, you are right.
So how it could be make the model improve the quality or performance?
You mean if you want to compare instead with one layer neural network compared with the two layers neural network? I think it's different because when you train the sparse coding, we need to impose sparsity in this first layer. And the observations are incomplete. So for each data samples, you need to mask the pixels that you have not access to. So it's not easy to compare the two situations. But I agree with you that using this prior model for data input, it's like increasing the complexity of the full model. So I totally agree with you, yes.
Thank you.
Thank you, thank you, good question.
Thank you. Let's thank Professor Caiafa again for his nice talk.
Thank you.
So the last session we would like to discuss, just have some open discussion. Here I list several topics we can discuss, but it's not limited to this. So first topic is in the era of generative AI, what are the core advantages of tensor method, like efficiency, explainability, reliability, or actual. A second topic is what are the fundamental challenges from theory or from applications to be addressed in tensor-based machine learning. And in the topic 3, in which interdisciplinary field do you think tensor learning is most likely to have a disruptive impact in the future? Like generative model or quantum computing, trustworthy AI, or tensor for science, and so on. So besides this topic, you are free to discuss also something else, like how we pursue the collaboration in the futures, and yeah, anything. Yeah, please feel free to share your opinions, and let's do some free discussion. So maybe Professor Li Qingzhang, so you are my supervisor, can you?
So, okay. Yeah, these quite challenging questions for discussion. First of all, I believe that tensor is natural structure in our brain. In our brain cortex, for visual cortex, from layer to layer, and we know that is one layer is a matrix representation. Another layer is also matrix representation. The connection between layers is tensor, not matrix. It's 4-dimension tensor. So this structure is a natural way that our brain developed from 10,000. Why brain evaluate in this way? And I think there must have some advantage. We need to further explore that for our computational model. This is the basic structure. Second one is that now we are in the large model era, but we still lack of knowledge. The large language model is actually data-driven, but at least at this moment, I think there's still lack of logical inference. The kind of causal inference, or what kind of the variable or explainable inference. So the first step for future challenge, fundamental challenge for this is, I think we learn some model from our brain structure. We still need learn the behavior of human life once we grow up, and then for children have to learn one object, another object, and learn logical by first starting by counting. The machine should also learn the way human learn. So the concept is very, very important. So for some others, for tensor model, what is a destructive impact? I think at this moment, I don't have a good idea. At least I think the tensor is a very good model for developing a model for especially for learn some concept of the concept-based learning model. Okay, that's just my opinion for this.
Thank you for sharing your opinion.
It's very interesting. So I do believe in tensors, obviously, especially now with terabytes models being prominent and so on. The issue is that most of the time we use tensors either as a pre-processing or kind of post-processing model. And that's fine. We reduce dimensionality and we have some interesting representation. We find structure in data, maybe we remove some noise. But the question is it possible for tensors to be an integral part of learning? And I think that's the issue partially mentioned by Cesar here. Can you have joint optimization for representation and learning? The second thing is your data. They can be either naturally tensor data, like RGB images, for example. So RGB video is then also a tensor. If you add, obviously, sound, that's another dimension, and so on. So in my team, I think 5 years ago, we developed tensor backpropagation. So you can train neural network which operates on tensor data, but somehow it kind of is gone almost completely unnoticed. I don't know if there's appetite for that. And the issue is that we have 2 or 3 different communities talking together. So in this community here, we have learned a lot and borrowed a lot knowledge, a lot developments of tensors from physics. But physics people have no interest in black boxes. So they usually have no interest in say, neural networks. Then you have computing communities who are more interested in implementation, efficiency, rather than maybe mathematical development. And you have our community, which, so we come from the old guard where mathematical development is maybe more important than implementation. And somewhere there's actually a sweet spot. So to me, I haven't answered any of these topics. To me, it's very, very interesting to see if tensors or tensor representation or whatever you want to call them can become an integral part of learning, either through a new loss function or through completely tensor data or maybe some other way that I'm not aware of yet. Yeah, thanks.
Yeah, I have a question about you had some work using tensor to make model compression for ChatGPT. So what do you think about this direction? Will you still continue?
Yes. So it's one of those situations. So we were, I think, first to compress ChatGPT 2 using Tensor. I think Tensor Train it was, and we have not managed to publish it yet because we put it on the archive and then we submitted to NeurIPS, to ICML, wherever, and it got rejected. In the meantime, there's new LLMs, there's people doing similar things, and that's the actually very dangerous part of our job that's happening at the moment, because there's so much development that we need to sanitize somehow the way we publish, because there's hyperproduction, and as soon as you put something on the archive, it's not yours any longer, obviously. So anybody who has a better computer or maybe bigger team or whatever can take it further. And I'm glad you mentioned that, because I'm toying with an idea of having a very rapid way of communicating new discoveries, something like AI letters. And those AI letters, you would be able to get your feedback within a month or 6 weeks and publish, if it's worth publishing, within 3 months. And it's a core idea, maybe 4 or 5 pages, which does not prevent you then from expanding, extending, and submitting to all those top conferences or top journals. And I'll be very interested in hearing from you whether there's an appetite in the community for that type of rapid publication. Because for many reasons, okay, in RIKEN, you have mostly postdoctoral researchers, but also PhD students. PhD student needs to graduate. For them to graduate, they need papers. For their future employment, they need papers. And I have a wonderful student. I mean, she developed with my team ChatGPT, and simply she has not been able to publish it, and it's been sitting there for 2 years now. Now it's totally out of date. And then I don't have, and I don't want to use supercomputers. I don't want brute force. I think that's unnatural for this type of community. You want to use frugal models, you want optimization, and so on. And it's not only my team. There's many people around who basically were left out on the dry with some wonderful idea in its initial stage, which you could develop maybe on a server rather than using supercomputer. And there's this kind of disparity now between university and all those big companies, because we can't really go into that scale of simulation. So to this I'm converging maybe towards the idea we need a means of rapid communication where the core idea would have a theoretical component and very basic simulations to basically confirm the theory, maybe once on synthetic data, one on real data, and so on. I'm a little bit concerned that these days, and then I'll give the microphone away because I like talking. I'm a bit concerned that these days, for example, my students submitted to IEEE PAMI, and nobody questioned the algorithm, and the simulations, in my opinion, were sufficient to demonstrate what we did. So the review process, nobody questioned anything. They just wanted more simulations. Because when he submitted, it took 1.5 years for the reviews to come in. In those 1.5 years, you have new benchmark data, you have new benchmark algorithms and everything. So he spent 3 months full time on many computers simulating. Then he submits the revision. In half a year, there's a new benchmark, there's a new state of the art. You cannot change, I mean, it's an endless game. So I'll be very, very curious to hear from you guys how you feel about having something in terms of rapid communication where you can stamp your authority on a really good technical idea. Thanks a lot.
Yeah, thank you. Yeah, it's a very common problem. I think now AIP have a RIKEN server, but before the deadline of conference, usually it's very crowded, and we cannot perform the experiment in a very fast way. And now the reviewer always asks many experiments and a huge, I think it takes huge computational time. So anyone else?
Sure. Because I also worked on tensors for years, many years. The first topic is how to say, today we have a lot of talks focused on this problem. I already explained a little about this topic. We have showed that tensor methods have some promising and in efficiency, explainability, reliability, etc. I want to share my very shallow understanding about the second topic. I think, for me, I think the bottleneck is computation efficiency. Why do I say this? Because if we, for example, we compress a network using tensor methods, but after that it's true that we can reduce the number of parameters. But if we implement this model in practice, it often requires more time to run the inference network. I mean, so far, if we decompose the tensor, we need more time to, we need a lot of work to determine the rank, and also find a very efficient decomposition method. And if we reconstruct the whole tensor, it also need a lot of time, especially the contraction operator often consume a lot of time. In this case, we no matter how many new methods we establish, but when we implement in practice, it also always like how to say, it's alternative, not indispensable. We always can find another way, use a matrix or vectors can achieve the same goal. I think this is how to say, sometimes a little disappointing. This kind of efficiency, I think, is very important. We should, how to say, in the past, we can publish a lot of paper and show that we have some, how to say, improvement on the efficiency or time, etc. But that's really not enough. In this case, I think we hope that tensor method is like a killer, not just the alternative. I think this I hope in this community, a lot of us can devote to in this area. Really, for matrix and the vectors, the fast computing is supported by the chip and generally very efficient. But for tensors, it's far behind this one. So I think if we hope tensor methods can be more powerful in the future, I think we need to break through this bottleneck. And it's my very shallow understanding. Thank you.
Thank you for sharing.
It's so nice to hear many views from all the professors. I would like to express my viewpoints on these problems from some sense of mathematics. In my opinion, I think tensor methods is a kind of algebraic methods. It shows us a very good way to imitate the natural world, including the matters and the events, how the matters organize, how the events comes from one to another. I think it used the perspective of the discretized points, the discretized ways. I think usually we can see a problem in the perspective of discretized way, like algebraic way. We can see how things connected to each other. This is my point of tensor or matrix tensors. I think if we go from discretized to continuous, in fact, tensor is a function of multivariable. Is that right? Okay. If we go to infinity, go to continuous, tensor is a function of multivariable. But for tensor, for the algebraic way of tensor, like tensor decomposition, we can do tensor eigenvalue, tensor eigenvector decomposition. Then it's different. We cannot do that in continuous way. In my points, I think we can combine two perspectives from algebraic way and from with the continuous way. For continuous way, we can do calculus. We can establish partial differential equation. We can establish differential equation. I think we can combine two ways. Maybe we can, it's easy for us to find the nature of the outer work. Okay, this is my point. Thank you so much.
Yeah, thank you. Thank you very much. Yeah, anyone else?
My question, so it's not so much about research, but about education. So how do you introduce tensor methods within a curriculum for students in computer science? So at some point, students, they are courses, or it seems like we have object-oriented programming, functional programming, like almost like tensor programming. So I would like to know, like here or in other universities, so how do you introduce tensors at the undergraduate level and or at the graduate level?
Yeah, so far, every year, AIP have a serious lecture given to University of Tokyo. And I think AIP choose 10 team directors to give a lecture to University of Tokyo. And mostly master students and the PhD students will join the lecture. For undergraduate students, I'm not sure if the University of Tokyo have such lecture to teaching tensors or not. But for sure, it's in quantum physics, tensor network is one of the most important tools to handle the many-body system and quantum computing or something. From physics side, they know tensor network very well. But in computer science, I think it's not so popular. And especially in machine learning community, it's very few teams in the whole world are working on this topic. And we try to find some potential importance of tensor method for current machine learning and AI. Yeah.
So do you see that it's an obstacle for the community that there are no particular topics that are taught at the undergraduate level, so to encourage undergraduate students to pursue tensor studies at the graduate level?
Honestly speaking, we don't have much focus on education because RIKEN has no students. So RIKEN is a research institute, so we only have researchers and we don't have students to educate.
But when they come, do they
Yeah, they come as interns, so they work for RIKEN.
So prior for coming, so they have no idea about what is a tensor or tensor theory?
Yes, when they come, we have many discussion or team seminars. We can educate.
Okay.
Yeah, partially. Yeah, sure, please.
I also think that it's kind of a little bit of a mission of this community to popularize tensor methods. Because when you see an old-fashioned paper on tensors, you see all those indices and products and sums. It's a little bit, looks difficult, off-putting for people. I think it's our duty also to clarify many things, maybe using graphical tensor representations so as to attract more people to tensors. Everybody knows that tensors are the future. But even TensorFlow is nothing to do with tensors. So I think that we need one killer application, whatever that is. Maybe it's tensor and quantum. Maybe it's tensor neural network, fully tensor. And I think Richard mentioned that for images, high-dimensional neural nets, the kernels are tensors. Maybe we need to do something about that. The other thing is that this linear algebra is part of the curriculum in all basically engineering fields and computing fields and mathematics and so on. But multilinear algebra is not. So in my course on machine intelligence, I can only do maybe 2 hours lecture on tensors. And all I want to do there is just to tell my students that, hey, if you really want to do hardcore, proper, long-term research, this is the way to go. So I can generalize all these SVDs from linear algebra to Tucker and all the rest and show a little bit of compression and all the rest. But I think that it's a little bit up to us to shout out a bit loudly. Because in machine learning, all these new heuristic algorithms, whichever, UNet, ResNet, whatever, it's all heuristic, but it works. So in machine learning, the current state is you produce something in a heuristic way, and you beat state of the art, and you give it some bombastic name, HammerNet, or I don't know, whichever net, and you go out and shout very loudly, wow, my network is the best. But we don't do that. I think we should be much louder. And the second thing is, or third thing, and maybe that's good, that all these big companies, Google, Amazon, all the rest, I'm sure that they're playing with tensors, but they have not put anything out public yet. So one killer application, maybe some of those posters we saw here, that would be attracting lots of people to tensors. But mind you, so at the university, our kind of product is a graduate student. That graduate student needs to find employment. If they work in these days, if they work in something which is considered difficult like Tensor, they maybe won't be able to publish 4, 5, 6, 10 papers like if they train neural network. That gives them job in Google. So we need to think a little bit how to kind of humanize tensors. And I think it's our responsibility. It's my fault as well. I haven't promoted them enough. And Chibin's team has been the leading tensor team for the last 10 years in the world. And I honestly think that with one killer application, then the situation changes totally. Yeah.
Yeah, agree. Okay, maybe it's time. It's time to finish. So finally, I would like to appreciate all of you to give a fantastic talk. And I think we had fruitful discussions, dinner, workshop.